welcome to one and all watching this video. So here's me presenting to you our official GitHub repository of our team's presentation B3 and KD3 under the organization Cybersecurity DSA. You can access this repository under this organization. So yeah, I'll just take you through our repository now. So yes, I will just directly start with the team members and roles assigned in our project. So our team is a team of 11 members. Uh, our team's project manager is Akshay. Our team's business analyst is Sindhamaraikanan, and developers are myself, Jayalikaji, Kirtivasan, Shreyas, Amin, Divesh, Harish Raghavendra, and the testers include Adityan PU, Lakshman BS, Bala Vigneshwar. So yeah, let's start with the presentation designed by our project manager. So yeah, it's loading one second. Yeah, so this is our data structures presentation. So this is our registration numbers, our name and the roles assigned. And then, yeah, so this is the major contents, the project, implementation, applications, process of implementation, roles and development processes, conclusion. So then the project contents that include from basics, what is a B tree? It's just a self-balancing tree where B stands for branching factor. And then the basics, it comprises like the nodes, the root value, the internal nodes, the leaf nodes, the key values, child pointers, etc., whatsoever, which will be explained in the code very soon. So these are the formulas to calculate the number of keys and number of children from, it ranges from B minus 1 to 2B minus 1, and the children ranges from B to 2B. So this is a simple B tree with order 3. So the next one follows is KD tree. KD tree is again a binary search tree. Here the major thing is that the comparison of the coordinates that's used in the KD tree occurs depth-wise. Okay, so this balance structure also enables efficient search, insertion, and deletion operations also. Some of the common applications include KNN algorithms in machine learning, such as nearest neighbor searches, range queries in distance formula, etc., particularly spatial indexing. So the implementations part. So just I've given access here inside the presentation. It will take you to the repository. So yeah. So the thing to add is that the timely developments in the Gantt chart. The Gantt chart includes the developments and the individual contributions by each members in our team. That's designed by our project manager again. So you can see the timely updates of each operations implemented in both the trees, B tree and KD tree, on particular dates whatsoever. And then again, these roles of each one allotted. So the Gantt chart includes the contributions of each operations implemented. So these are our names, myself and Namin, Kirtivasan, Bala Vigneshwar, all of the individual contributions. You can access it through the repository. I will not take much time for this because we are allotted just a period of 10 minutes. So then I will directly take you through the code now. So before taking you to the code, I'll just show you a sample KD tree. So this is a sample KD tree. KD tree means it requires two coordinates, okay, X and Y. Basically, it works on spatial indexing. So the major concept is that the key value, if the key has a depth of even number, that is the first, this root node has a depth of 0. So again, that's an even number. So the comparison occurs X coordinate wise. So you can see if you're trying to insert 5 and 25, 5 is less than 30. And as I said, it's a simple binary search tree whatsoever, right? So the comparison occurs X coordinate wise, so it gets inserted in the left side, in the left subtree, okay? And then for the next node, that is 525. If you are saying now the depth is 1, the depth is calculated by number of edges, right? The depth is 1 now for this key. So then the comparison occurs Y coordinate wise. So 12, if you're trying to insert 10 comma 12, now you have to see the Y coordinate. Y coordinate, if you can see, it's 12, and the 12 is less than 25. So again, it's getting inserted in the left subtree. Same logic works for the right one, and again the 50 comma 30 insertion and 35 comma 45 whatsoever. Now I will call upon Keith wasn't to explain the code. So this is a simple 2-dimensional KD3 implementation code. So yeah, over to you, Keith.
And the KD tree code, so we have included the headers IO stream, math.h, stdio.h, chrono, all those basic headers, and chrono for the runtime calculation, and math.h for some math parts. And as we know, we are going to insert point, that is the coordinate. So we have created a struct point where it stores the x coordinate value and y coordinate value, and a node to store it in the KD tree. The node contains the key value. The key value is nothing but the point, and a left and right, a pointer to the left and right child. And then we have created a class for the KD tree, which has a root node in the private the private with the private label. And then the public, we have the functions like kd tree, that is the node initialize sorry class initialization function, which takes two values and then puts it to the creates a node using those two values, and then points it to the root variable. And then get root function, it returns the root. As you know, we are going to do all the operations of kd tree based on the root value, so we need to get the root from the class. So we are defining a function get root to return root. And then insert, it's a void function. What it does is it gets the value of root, and then the value 1 value 2 is the x coordinate value and y coordinate value, and the depth, which is by default 0. During the function call we mention it as 0, and then it inserts based on the logic of the kd tree. And the next function, yeah, next function, it's the find min. The find min actually finds returns the leftmost node in a given tree. So it finds the leftmost node. It's actually used in the delete function, and the delete function, it returns a node. So it takes the root, so the row node root value as parameter, and also again the value on value 2, which is the x coordinate value and y coordinate value of the node which is to be deleted, and the depth, which is by default by 0. And then based on the kd tree deletion logic, it deletes and then returns the updated root node. The next function is traverse. It's a void function again. It takes the value of root and then traverses the tree. So the traversal is pre-ordered traversal. And the search function, it takes the value of the root and then the value 1 value 2, which is again the x coordinate and y coordinate. What it does is, it's the given point, it searches whether the given point is present in the tree or not. If it is present, it returns true, that is it returns 1. Else it returns false, that is returns 0. And then 2d print function, so it is to print the all those points in our terminal, in our output screen. So this function is for that purpose. So it prints like how the points, if they are plotted in a graph, how it looks like. So the same way it prints in the terminal screen.
Right, Keith, awesome. Thank you
And
for
then
that.
our class
And then in the
exits, and it is the
yeah,
we are having the main function here. Here we have made a menu driven interface where we have printed all the options, and we get the choice of the user, and then make appropriate function calls.
okay, just to add to Keithi's words, we have just included the chrono module so that calculates the runtime complexity of each function inside the code. I'll just run the code now. Uh, so let's go to compiler. Yes, let me just create the root node first of all. So these are the values. As you can see, the root node 30, 40, and then I will start insertion node. So this is for time taken for the creation of root node 30, 40, and then I will start inserting now. So the values say, as I say, 525. Again, let me insert 70, 70, and then let me insert uh, 10, 12. Basically, it takes two values, as I said before, so, because a key requires two nodes, right? So then 50, 30, and then 1 again. So the last key 35, 45. Now I'm willing to print the result in 2D. So let me give the choice as 5. So as you can see, 30, 40. 30, 40 is the root node. It's just the graph is tilted. Okay, I mean the tree is getting tilted to the left. So 30, 40 is pointed here. To the left you can see 5, 25, and to the left of 5, 25 you can see 10, 12. To the left of 5, 25 you can see 10, 12. And to the right you can see 70, 70. To the right you can see 70, 70. 70, 70 is left side, you can see 35, 45. I didn't insert 50, 35 or info. So yeah, tree is getting printed correctly. I will implement the delete operation as well. So I'm trying to delete the node present in the tree first. So yeah, time taken for deletion of node, it's 0.00 something 9 seconds. And then say if I'm trying to delete a node that's not present in the KD tree, let me give a value of 5, 20 for that matter. Yes, it's not present, so I'm giving a simple traversal now. Time taken for traversal, as you can see, the 5 comma 25, that node, it's deleted and it's not getting printed in the traversal part. Now if I'm again willing to print it in 2D, this would be the output, and then I'm exiting it now. So this is a simple implementation for the 2-dimensional KD tree. Now we have designed a simple application for the KD tree part. So that takes an extra function. So this is, as you have heard, it's KNN algorithm that's used in machine learning. So it's used for searching nearest neighbor searches. Now I call upon Keith to just explain the function alone, the distance function.
So this application uses the KD tree. So whatever functions we have created for KD tree, the same thing we have implemented for this too. And the functions which are extra is that we have added a distance function. So this function returns the distance between 2 points. The parameters of this function is two struct point structures. So we have to pass on the point structure to the to distance function. It returns the distance between the both the points.
Yeah,
And
basically
then
the
J has
distance
to
of
move
the
over to the
yeah
nearest neighbor function.
yeah. So basically the distance of the query point from the node point. Okay, that's present in the tree. Now I'll just move up on to the distance function. One second. So print nearest neighbor. So yeah, Kirti.
Yeah, the nearest neighbor function, it returns struct point and it takes the root node of the tree and then the a b value, so which is the uh, x and y value of the point to which we have to find the nearest neighbor. And node current, it is the current that is the current node which has the nearest, which is nearest to the point. And depth, which is as usual, it's going to be 0. So these functions calculate for traverses through each node and then calculates the distance between the given point and the current node's point value. And then it returns the best, that is it returns the nearest neighbor's value as the structure.
Yeah.
In
So in
main
layman's
function,
terms,
we access the variables in the struct point and then we print the value.
yeah. So in layman's terms, it just traverses through the entire nodes. Basically, checks the query point is nearer with which point in the KD tree that's present. So I'll just run this sample code now. One second. So this is for checking nearest neighbor. So this is just an extra function that's been implemented in the 2-dimensional KD tree that's been already shown to you. So I'll just create the node again, say that's 30, 40. So the node is created. I will just insert it now. 20, 30, say random nodes 40, 56, and then some other random nodes say 67, 89. So then I'm trying to print the result in 2D. Okay. Now, as you can see, the menu-driven interface offers me a choice of 5. So find nearest neighbor. So I'm giving a choice of 5 myself. So then say out of these points, say I'm giving 21, comma 32. So it should be nearer to 20 comma 30. Basically, this query point has been checked with the points of the KD tree using the distance formula. Basically, the simple formula that's the root square root x2 minus x1 the whole square plus y2 minus y1 the whole square. So this is the basic application that we have designed for the KD tree. So yeah, now I will take you through B tree now. B tree implementation. So yeah, I will call upon Keith Vasan to explain the code.
Here in B-tree, we have included the necessary headers. That is, we have included the basic headers like IO stream and stdio.h, and also we have included the vector and queue, which we are using because we have to store some not a we have to store some multiple values. So for that purpose, we are using arrays and also the vector, which is in the STL library of C++. And the struct node, the declaration of struct node, you could see, and it has an array of keys and then the number of keys present in that node and whether the node is leaf or not. To represent that, we are having a boolean variable leaf, and also we are having an array of the child pointers. And then first, the function here, it is a create node, so it is to create a node in the b tree. It defines whether the node is going to be a leaf node or not, and then also it mentions a degree. So based on the degree, we know that it finds how many number of keys can be in that node. And then next, it's search. The search function, it gets the value of the root and then the key to be searched. And then what it does is it first goes to the root node, searches in the root node, and it goes to the first child pointer and then searches in that child. And then again it goes to the child pointer of that node, and so recursively it searches in the child pointers and then comes back. And then this is how it searches. And then split child. So split child function, it is called when the maximum number of keys in a node it has reached the maximum capacity. If the node has reached the maximum capacity, then if we need to insert another element in that same node, so at that time we split that node, and for that purpose we are using the split child function. And then the insert non-full, it's actually utility function for the insert function. And this is the actual insert function which we are going to call in our main function. And this inserts, and if suppose if we need to split the node, it calls the split child function also, and also the insert non-full function in order to insert in the node. And then traverse, as usual, it traverses through the children first, like it traverses through the root node and then to its children. And then if that child doesn't have any other child, it comes back to the again to the root node and then to the next child. So recursively it happens. And then the print 2D util function, so it is used in the print 2D function. It is called by the print 2D function, and print 2D util function is used to in our terminal. And the main function as it displays all the menu, and then it gets the choice from the user, and it makes the appropriate function calls. And also we have used the chrono library to calculate the time taken by that function.
Yes, I will now show you the runtime as well as Kirti mentioned it now. Yeah, one second. Yes, I'll just run it now. Enter the degree. Let's say it's 3 now. So it has a choice of b to 2, sorry, b minus 1 to 2b minus 1. So 2 to 6, 2 to 5, right? 2b minus 1, 2 times 3 minus 1 is 5. So then let me insert the node, the 10, and then time taken for insertion of node 10. Each function, again, same thing as KD tree. We have included the chrono module. I will just take a short time to implement all the nodes. Yeah, just add everything. 67. And then I'll just search. I'll implement the search operation to search the node, say 67. That's found, key found. Let me just search a key, the node that's not present in the tree, say 68, that's not found. So it's working. And then I can implement it with the traversal also, that's in order here. So 10, 35, 45, 67. And then I can print you the result in 2D as well. So yeah, this is the printed result in 2D. Okay, so basically, let me explain them. So this is a simple B tree. So as I said, the traversal is in order now. So how the search operation will be implemented is that it first has to traverse in order. So left, root, right, right. So 5, 10, 15. Then it doesn't find any children, so it has to come up again up till 10, and then it moves to 20. 20, it finds 30 in between. Okay, so 30, and then it traverses to the left subtree. So it finds 25 and 28. You have to include for loops for these things. I mean, there is a reason it's of time complexity as well, but still, you have to look upon the left subtrees as well. 25, 28, it gets printed. Again, it moves up as it cannot find any children below. So it has to move up to 30. And then after 30, it will print 33. And then, after 30, it will print 31. And then no child is found. So it again moves up. So 33 is printed. And then it moves up. 40 is printed. 40 to 50 is taken. And then 50's child is found. Three children is found. So it first prints the left side value, then the middle value as left, root, right. So it follows the in order traversal. So 50, 45, 45, no children is there. So it again comes up to 50. And then 50, in between it finds 55. And then from 55, it goes to 60. 60 finds the children 65. Yeah. So it will be like adjacent, ascending order example for this simple by B tree. So this is simple README files that we have created for newbies who are trying to learn binary trees, B tree and KD trees. So yeah, from basics we have implemented. I mean, what is it? What is the order? I mean, what are the parameters used? Nodes, leaves, whatsoever, with some formulas such as b minus one to two b minus one. And we have inserted few examples as well. And then same goes for KD tree. We have included what's so necessary, like the dimensionality, splitting access, splitting value, balance structure, leaf nodes, whatsoever is necessary, and some applications such as space partitioning and spatial indexing for that matter. And then implementation basically, as I gave you an example of inserting two keys, right? Key values 30, 40, 35, 45 in my code. So same thing is given here. So yeah, and then the test cases. So thanks to Harish and Divesh for helping me with the README file implementations, and then documentation basically by the business analyst Senda Marikannan, and Shreya has also played a important role in preparing this documentation. So I will just show you the documentation now. We have just discussed the best case, worst case, and average case time complexities in our documentation of each function of KD trees and B trees. So as said, the evaluation criteria is based upon the running time of each function of compared with different sections, right? So that's been checked by the testers. But the thing is, the issues between the developers testers, that's been sorted out by Shandamare Kannan. So some of the issues that we faced are we couldn't implement delete operation in B-tree for that matter. And then while implementing delete function in KD tree, we initially did used void function. Because of that, we got garbage value in the node deleted, rather than deleting a node that's not been present in the tree. So we got several misses with the boundary conditions. So this is basically all time complexity analysis for basically insertion, best case, worst case, average case, deletion, best case, worst case, average case. Time is limited. I'm not taking much time. Everything is included in the documentation. You can view it to the repository. And then two applications of KD tree is given: nearest neighbor search, range search. Everything is given. Pseudocode is given for the search implementation. And then same goes for B tree as well: insert, search, traverse, print. Whatever we have implemented, we have given in the documentation. And then some applications such as file systems and databases. So yeah, I'm closing the documentation. It's accessible, as I said, inside the repository. So now I'll just take you to the test cases. Test cases is just sample in output checking. So yeah, thanks to the testers Bala, Adityan PU, and Lakshman BS for helping us with the output cases. So we have just checked the outputs, whatever is inserted, whatever is deleted, whatever is searched, and we have checked the 2D printing formats as well, everything. And then finding nearest neighbor cases, or for everything, for finding nearest neighbor B-tree and KD tree. For all the three, you have tested all the outputs. And then the boundary conditions, as you can see, let's check the boundary conditions I have given. If you're trying to delete, say, a node that's not present in the tree, it should not disturb the functions that's running outside, like the traverse function. I mean, there is no relation, right, with the node you're trying to delete that's not in the tree to the traverse operation. So that's one boundary condition. Again, that's not disturbed. We have checked that in the output as well. So yeah, that's been listed here. So the boundary conditions are not disturbing the runtime of the traversal function, basically. So the boundary conditions are handled basically. And whatever is possible with the finding nearest neighbor test cases is same as with KDT test cases, because only one function is extra that we have implemented. The nearest neighbor search is basically based on the distance formula that is present here. So this is our repository documentation by the business analyst and Amare. Project manager did the presentation. And for the contributions, timely developments and contributions, you can check the Gantt chart over here. And then the code developed by us developers, and then the README function for the code for newbies trying to understand about B trees and KD trees, and the test cases. Thanks to the testers for doing it. So once again, I'm grateful and fortunate to be part of this amazing team. Yeah, so that's all about our presentation. We're willing to hear it from you in the YouTube video comments. Thank you all.